Do 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 do. Ice, ice, baby. Hey folks, this is part one of a three-part series where we will be going through icebox problems, encountering three different scenarios and what those types of questions can look like. So in general, just to explain what an icebox is. An icebox is where we take some sort of chemical equation and we make a chart that looks like this for ourselves, where we have I, C, and E, and then up above we'll have whatever our reactants are, turning into our number of products. And so an icebox is designed to tackle three different things. It's designed to look at a reaction and say, what will the concentrations be at equilibrium based on this KEQ? Or if these are the concentrations at equilibrium, what is the KEQ? And those are types of questions that we'll encounter. For this one here, when we set up the icebox, the I stands for the initial. So whatever we have initially, before we actually start reacting stuff, those are the concentrations that we'll fill in there. And one of the key things is that this column is always filled in molarity. And the same goes for this equilibrium part as well. Our units that we always want to have represented, equilibrium, spelling's tough on a Monday morning. We always want to have the I and the E represented in equilibrium units. And so sometimes you'll be given a question and it'll say, hey, you have this number of moles in a, let's say, 2-liter solution. And what you'd need to do is say, well, we need to take those number of moles and divide that by 2 liters, and that will give us our concentration in molarity, which is represented with a capital M. The C in this graph is the change. And so a lot of times what we'll see is this will be a plus or a minus X, or a plus or a minus 2X. And this is the overall change in concentration that we're seeing. And what we'll use here is we'll use the balancing coefficients to determine if we need to use a 1x, a 2x, a 3x, a 4x, etc., etc. And we will fill in that column there with those balancing coefficients. And so whenever we start off an icebox problem, we're always going to fill in the information that we know from the question in the initial part. The changes after that we'll fill in with an x value, and then the equilibrium, again, we always want that to be in molarity. So we have our first example below here. Ammonia is created by the following process. N2 plus 3H2 goes to form 2NH3. And how I always set up my icebox is I always rewrite the actual expression itself, 2NH3. And then what I do after that is I start to fill in the actual icebox itself. And so I'm going to use actual lines here just to make this look a little bit neater for us. 1, column 2, column 3, like such. And then let's extend this line down a bit more like that. Let's extend this line a bit more like that. All right. So we're going to have our icebox here with I, C, and E, just like this. And we're going to break these all up into little sections like this. And so I like to put the reactants and products up top so that I know exactly what column it goes in and what exactly reactant or product I'm talking about. So here in our question, we say initially the concentration, square brackets are used to indicate concentration. The concentration of N2 is 0.96 molarity. So initially we know that 0.96 molarity is the concentration of the N2. And H2 is equal to 0.72 molarity at equilibrium initially. And then at equilibrium, we know the concentration of NH3 is 0.24 molarity. And so one of the assumptions that we need to make always whenever we're tackling these questions is we need to assume that we are starting off with 0 molarity of this product. We need to assume that, well, we're starting with 2 reactants, we're throwing them together in a beaker, it'll be a closed system, so no outside influence at all, and we're going to start with 0 of the product. That's an assumption that we have to make to solve this problem here. Now, what we can see is we actually know one of the pieces of information at equilibrium. We know that this NH3 went from 0 molarity to 0.24 molarity. And so what we need to fill in is this change column here. What I'm going to do is I'm going to take this balancing coefficient of 2 and say, well, in order for this reaction to happen, I need 1 mole of N2, 3 moles of H2, and 2 moles of NH3. So what we should say then is for every one thing or 1 mole of N2, we should have twice as much NH3. And so what we're going to do is whenever we have the products, those are always going to be plus, right? We want to go from 0 to having some amount of stuff. So we're going to add stuff in. And the reactants, we're going to take some stuff and take away from it to fill in that chart. So 0, and we're going to use that balancing coefficient to go plus 2x, and we know that that equals 0.24. And then what we can say is, well, because we're talking about moles in each one of these cases, 1 mole for the N2, 3 moles for the H2, 2 moles for the NH3, we can use X's for all 3 of those categories. And so we can say that, well, N2 would be a minus X. We want to use some of it up, and we want to use X amount, or this many moles amount, to get to our equilibrium state. For the H2, it's going to be minus 3X. And so what we need to do then is figure out, well, what is this X value? What is it worth? What we know is that 0 molarity, what we started off with, plus 2x was equal to 0.24. So because we have a 0 molarity, what we can do is just cancel that out of our equation. We now need to get this x by itself, so we'll divide both sides by 2 here, and we end up with x is equal to 0.12. And so what we know then is that we can fill in that 0.12 for each of these values. So we'll have 0.72 minus 3 times 0.12. And here we'll have 0.96 minus 3 times 0.12. Sorry, not 3 times, just 0.12 minus 0.12, like that. Okay. And so when we actually fill these out, we can see that we're going to get 0.84 molarity for this block here. We're going to get 0.36 molarity for this block here. And we knew that this 0.24 was the final value. And so we ended up solving here for this 0.84 and for this 0.36. And so those were all 4 of the columns that we filled in. So this is how you calculate, using an icebox, how you calculate equilibrium concentrations using known values. Now, we haven't actually answered the question yet. The question was, what is the equilibrium constant? And so what we need to do then is take our chemical equation and take the information that we had, and we need to make a KEQ expression. KEQ always being concentration of products over reactants. For this one, we'll have the concentration of NH3. And because it's a balancing number of 2, we'll need to square that. And then on the reactant side, we have N2 and 3H2. So we'll have concentration of N2, concentration of H2, and we will cube that. And that'll give us our final answer once we plug in the numbers here. So the reason that we needed to solve for those numbers was we want to find the constant of equilibrium. In order to do that, we need to have the concentrations at equilibrium. And so we can plug in these numbers here, and we'll plug in the 0.24 squared up top, put brackets around that. And then we have on the bottom here the 0.84, which is not squared at all because it's the N2 concentration. And then we have the 0.36. And we are going to cube that. And when we finally solve, we get a final answer of a KEQ is equal to 1.4697. And we'll put a box around our answer. And that is how you solve for the equilibrium constant expression when given known equilibrium values. And that is also a general explanation of what ice boxes are as well. Hope this was clear. Let me know if you have any questions at all.